Alright guys, here's our first video lecture, starting in section 3.1. And just some housekeeping before I get started with this going forward. You'll get the benefit now of my handwritten notes. I'm limited with what I can do here at home. I don't have the tools or the time to do some nice, neat, typed up notes and all of that, so you get my handwritten notes. But I'm going to go through these, read them out, just make sure everything is clear. Also keep in mind, since you do now have the ability to pause and rewind and replay and all of that, I'm going to go through this rather quickly, so I don't have to spend a lot of time, repeating and waiting for responses and that kind of thing. So I'm going to go through them. I'll elaborate where necessary, and then we'll work out our examples, as we do in a typical class meeting. And so, of course, if you have any questions, need any further explanation, you can email me, or make use of the Ask My Instructor option on MyMathLab. We're available. I know not all the problems have that option, but make use of that where it is available. If it's not, then you can still email me, ask me to look at a particular question, and give you an explanation on what to do with it. So that's what we're going to have to do going forward. As I'll get these posted on a regular basis. My recommendation as I had an email is just I would spend time with these as you were attending class. Sit and go through your notes, highlight, take additional notes as you need, but I'll have the examples worked out for you on here, so you'll have that for reference. All right. Okay. Now we had gone through this, or at least did an intro to this section on that last day of class, this section 3.1. So I kind of gave you the gist of it, the idea of what we're dealing with here with the using the first derivative to determine where a function is increasing or decreasing. Also keep in mind though that we're going to make use of this going forward in application type situations. So it's not just going to be a discussion about the graph of a function and determining where a graph is increasing or decreasing. That's all fine and well, but how can I make use of that in the context of an application, to give me information about a specific situation. So that's where this is going to be useful going forward. All right, so let's get all the tools in place, and then we'll put it in practice. So recalling, from algebra, and again, I'm just going to go back and discuss everything we talked about that last day, just to make sure we're on the same page. So recalling from algebra, so we talked about linear functions and how our linear function f of x equals mx plus b, right? Where m is our slope, it's the rate of change of that function, right? And it determines the direction of the line, it determines the direction of the graph. Right? So we have positive slope, we have an increasing function, negative slope, we have a decreasing function, and we also have zero slope, where our function is constant. Right? And since the derivative of any differentiable function represents the rate of change, then we have the following theorem that we can apply to any function. We can let f be differentiable over an open interval I. Then f is increasing over that interval if our derivative is positive. So again, just like our slope in linear functions, our rate of change is our derivative for any function. And if that rate of change, if that derivative is positive, then our function would be increasing over that interval. And then if f prime is negative, then our function would be decreasing. So f of x is decreasing on that interval if f prime is negative for all x in the interval. And so for example, just that little sketch that I have, where I have a function that's increasing, then decreasing, and then increasing, right? The basic shape of that function. We have f increasing on the interval from negative infinity to a, right, on this part of our function. And then we have our function decreasing between a and b, and then it's increasing again from b to infinity. Right? And so then using the derivative to describe that behavior, right? So we know where f is increasing, our derivative is positive. Where f is decreasing, our derivative is negative. Right? So we have these intervals where f is increasing and decreasing. So increasing. Also the tan lines. So if we look at the tan line to the curve at each of those points on the graph, All right, notice where the function is increasing, because again, remember we talked about initially with our derivative, the rate of change, that was the slope of our tan line, right? So if I looked at the tan lines as line tangents to the curve, then where the function is increasing, the tan lines would have positive slope. And that's not going to be absolutely critical for our discussion, but it kind of ties it back to our whole, meaning or discussion about the derivative, which is the slope of our tan line. And then where our function is decreasing, right, on that interval from A to B, our derivative would be negative. Notice, of course, our tan lines then would have negative slope, right? Now, what about what's happening at x equals a and x equals b? At those 2 points, maybe we could call them turning points on the graph, right? Where the function changes from increasing to decreasing or from decreasing to increasing. Right? So what about what's happening at x equals a and x equals b? Well, if we look at the slope of our tan line, right, if we drew a tan line to the curve at either of those 2 points, right, our tan line would be horizontal, right, because it's changing from increasing, and then we hit that point where the tan line would be horizontal, and then we're decreasing and then increasing on this side. So horizontal line, right, remember, has a slope of 0. So we've got a tan line with a slope of 0, horizontal tan line. So f is neither increasing or decreasing at those points, right? But we can at least give some information about the slope or the rate of change of the function at those points. It's 0. These turning points are going to be the ones that we're ultimately going to focus on, right? So where the function is increasing and decreasing, what I'm going to be looking for on the graph of our function are those turning points, right? So these turning points are what are called critical points on the graph of our function. And the x-coordinates of those points are what we call critical values. Right? So those are terms we're going to make a lot of use of. Mainly critical values, those are the x-coordinates of those turning points. The points themselves we'll call critical points. I'll have to reset that each time I go to a new page, so just bear with me. All right, so definition. We're going to let a number c be an element of the domain, of our function f. X equals c is a critical value of f, or we'll call it a CV, if either f prime of c equals 0 or f prime of c is undefined. Right? So we're looking for those points that could possibly be locations for those turning points, right? For those maximum and minimum values of our function. So where do we start looking for those? Well, we know they could possibly occur where the derivative is 0, which we saw in that previous example. They could also possibly occur where the derivative is undefined. Right? So it gives us points at least to start looking for critical points. Right? So the point CF of C is called a critical point. The value for C where the derivative is either equal to 0 or undefined is called a critical value. Now recall from algebra, we always refer back to some of our basic algebra, but recall back from algebra, the point coordinates x coordinates CF of C, right, is the location of a relative maximum value of our function if f of c is greater than or equal to f of x for all x near c. And then back to that little diagram that we had before, let me do just a little quick sketch on that, right? We had A here and B here. We had a relative maximum right here because within that region of the graph, that's the highest point, that's the largest function value on the graph of that function. So we call it a relative maximum. The other term we use there, we call it a local maximum. Right? So relative max or local max. And the point CF of C is a relative or local minimum, right, if the value of the function at C is less than or equal to the values of f of x for all x values near C. Right? So that's what happened at B, because within that region of the graph, that is the smallest function value. And f of C would be the smallest value of the function compared to all other values of the function near that point. And so we call that a relative minimum. So that's kind of the fancy definition for that. Basically, I mean, it's a pretty easy observation if you're looking at a graph in terms of where you have those turning points, whether it is a relative maximum like we have at A or a relative minimum like we have at B. All right. But this is giving us a more formal definition of exactly what a relative or local maximum and minimum is. Now, f can also have an absolute maximum or an absolute minimum. Right? So the local or relatives, that's with respect to just little regions within the graph or the function itself. If we're looking at the entire function over its entire domain, then the function, of course, could have an absolute or global, is the other word we use there, absolute or global maximum or minimum at those points. Now, in that case, if it's the largest or smallest function value for the entire function, right, over its entire domain, we're going to primarily focus on finding those local maximums and minimums. I mean, yeah, we'll be interested in applications where the absolute max or absolute minimum value of a function is located as well. But our focus for this section is going to be how do we find those relative max and mins, right? So it's all about the first derivative. Now, critical values are coordinates for those maximum and minimum points. Right? We call these extreme values, or extrema for short. So these CVs that we're finding, these critical values, those are potential locations. Those are possible locations for these extreme values, for these extrema, right? These relative maximum and minimum values of our function. So this first derivative test, so this is what all this was leading to. Right? So kind of just putting a formal wording to all of this. So the first derivative test, and this is a test that we use for finding relative or local extreme values. Right? We let x equals c be a critical value of our function. So that means we'll find the critical values first. Then f of x has a relative minimum at c if f prime changes from negative to positive at c. Right? F changes from decreasing to increasing. So what's happening at x equals b at the bottom, right, where f is changing from decreasing to increasing, and again, that means our derivative is changing from negative to positive. So I don't even have to look at the graph. I find those critical values from where the derivative is either equal to 0 or undefined, and then I check to see what the value of the derivative is on either side of that critical value. And if that derivative changes from negative to positive, then I know that there's a relative minimum at that point. And then vice versa. In the case of point A, f would have a relative max, like we do at A, if f changes from positive. F prime, changes from positive to negative. That's where we have our function changing from increasing to decreasing, positive first derivative to negative first derivative. Then we have the location of a relative max. So we have our relative max at x equals a in this case, relative min at x equals b. But I can make that determination solely from looking at the values of the derivative. I don't need the graph. All right, so for example, now looking at the graph of the function and determining where that function is increasing or decreasing, that's pretty straightforward. I mean, you can look at the graph and you can see just from the shape of the graph, increasing, decreasing, where we have turning points, relative max, relative min. Let's take it in the opposite direction. what if I have the graph of the derivative of the function? Can I make that same observation? But like we said, it's all about the value of the derivative anyway, and the sign of that derivative, or the derivative, or the first derivative, to be more specific, because we're going to talk about the second derivative in the next section. So where that first derivative is positive, we know the function is increasing. Where the first derivative is negative, we know the function is decreasing. And where the first derivative is 0, we know we have a horizontal tan line. That's our critical value, possible location of a critical point. So let's reverse the process. Look at the graph of the first derivative. Now, so the graph of f prime is given in this case. Use the graph to determine, the graph of f prime is given, use the graph to determine where f is increasing or decreasing, and the x values of any extrema, right? Any of our extreme values. And then we're going to see if we can sketch a possible graph of our function f, just based upon that information. Right? So again, this is the graph of f prime. And so I'm looking at the values of that function. Wherever f prime is positive, then we know our function is increasing. Right? So our function should be increasing on this interval from negative infinity to 1. That's where our function value, our derivative values are positive, which means the function is increasing. Also notice something else. Those values are positive, but as we get closer to x equals 1, the values of the derivative are getting smaller, right? So they are decreasing in value. Well, what does that mean on the graph of our function? Well, we know the graph is increasing, but we also know that it's getting less steep because the values of the slope, the values of that first derivative, are getting smaller. Now, when we hit x equals 1, right, f prime is 0. So there's one of our critical values, or in this case, the critical value of that function. That would be where f prime equals 0. And then once we pass x equals 1, the values of our derivative are negative. So that tells us the function itself would be decreasing. Now again, notice the values are negative, but they're also getting larger negative. And they're getting larger negative as we follow down the graph this way, which means the graph should be getting steeper, but it's steeper negative. Right? So then what we're trying to do is, okay, let's take this information and see if we can't sketch the graph of our function based upon that. All right, so we have f increasing on negative infinity to 1 because our first derivative is positive on that interval. F is decreasing on 1 to infinity because our first derivative is negative on that interval. We know f has an extreme value at x equals 1. Right? And we also know that on the graph of our function, that should be a relative maximum, because to the left of that, f is increasing, and to the right of that, f is decreasing. Okay? So we should have a relative maximum. So what would I do to sketch the graph of this thing? Well, follow the basic shape. We know that there's a turning point. We know there's a relative max at x equals 1. So what I'm looking at on the left side of 1 is a function whose graph is increasing. But it's also getting less steep, right? Because the values of the derivative are getting smaller. They're positive, but getting closer to 0. And then once we hit x equals 1, there's our turning point. And then once we pass x equals 1, we said our function should be decreasing because the derivative is bigger. And it's getting more steep because the values are getting larger negative, right? So that's using the graph of the derivative to actually sketch or have an idea of what the graph of the function looks like. Okay. Now, for the remainder of these, for the other couple of examples, we're going to focus on just finding the critical values. And so, taking the function, find the critical values of the function, make that determination as far as where the graph is increasing, decreasing, where we have those relative maximum minimum values. And so this is more of just the basic concept. All right, so for example, finding any critical values and relative extrema for the function f of x equals x cubed minus 3x minus 6. Nice little polynomial function. As always, polynomials are the easiest to work with. And so we're finding our critical values. How do I find them? Well, the critical values occur, we said, at either where the first derivative is 0 or where the first derivative is undefined. So we'll start by finding our first derivative. Right? So find f prime of x, set it equal to 0 in this case. Now, I don't have any issues with that being undefined. Again, that's another polynomial. So I'm setting the derivative equal to 0 to find those critical values. And then this is our basic zero factor property in this case. Factor the polynomial, factor out a 3, factor x squared minus 1. Setting each of those factors equal to 0, right? X minus 1 equals 0, gives me x equals 1, x plus 1 equals 0. Now, I don't worry about the 3 because 3 will never be 0. I only worry about those factors that have the variable. And any value of the variable that will make that 0. That's basic zero factor property. I also went ahead and found the points on the graph where that occurred. Right? So I would say x equals 1, x equals negative 1. Those are our critical values. Right? And then I have the coordinates of the points, negative 1, 4, 1, negative 1, negative 4, and then 1, negative 8. Now, on the right, since I'm interested in determining, now I know where the critical values are these locations of extreme values? Are these relative maximum or relative minimum values, or at least the locations of those points on the graph of our function? What I have set up on the right is what I'm going to call a test strip. This is a test strip for the first derivative, and I've indicated on that test strip where that first derivative is 0, at 1, and at negative 1 and 1. Right? So I indicated those on my test strip. And then what we do is we look at each interval separated by those critical values on our number line. And we take a test point from each of those intervals to determine the sign of our derivative between each of those critical values. So I take a point to the left of negative 1, and any point will do, any x value will do, because whatever the first derivative, whatever the sign of that is at negative 2, then the sign of the first derivative is always going to be the same in this interval. It can't change. The only way it can change is if it goes through 0, and that's at x equals negative 1. So we take a test point from each of the intervals that we have set up on this test strip, on this little number line, divided up by those critical values. So on the interval from negative infinity to negative 1, this first interval, I chose negative 2. Again, you can pick any number in that interval, and I plug negative 2 into the first derivative, because remember, we're trying to determine where the function is increasing or decreasing. So where the first derivative is either positive or negative. So I'm looking at f prime of negative 2. Now you can do this a couple of different ways. You can simply take negative 2, plug it into f prime, which is here, and calculate the value of the derivative. I use a shortcut sometimes if I'm looking at a function that is kind of in factored form, or maybe a fraction, numerator, denominator. And since we're really only interested in the sign of that first derivative, we don't care about the actual value of the derivative. All we care about is it positive or negative? Because we know where it's positive, the function is increasing. We know where it's negative, the function is decreasing. I don't care about the actual value itself. So you can look at the factored form, and if I plug negative 2, say, into x minus 1, that's going to give me a negative number. If I plug negative 2 into x plus 1, that'll give me negative 2 plus 1. That's a negative number. So I have a negative number times a negative number, which is a positive number. That's just an alternative way of doing it. It's a shortcut. If you don't like that, you can always take your test point and simply plug it into the derivative itself. Right? And that's easy enough to do as well. So between negative 1 and 1, I chose 0. 0 is always a convenient point to plug in. If we plug that into f prime, that'll give us negative 3, so that is negative. Plug in 2, that was my test point that I chose on this interval. Plug 2 into our derivative, we do end up with a positive value. Right? So again, the sign of the first derivative, I know that it's positive on the interval from negative infinity to negative 1. which means then our function would be increasing. And it's negative on the interval from -1 to 1, which means our function is decreasing on that interval. And it's positive on the interval from 1 to infinity, which means, again, our function would be increasing. So critical values, x equals -1, x equals 1. F is increasing on the interval from -infinity to -1. Decreasing on the interval from -1 to 1, increasing on the interval from 1 to infinity. And since we're changing from increasing to decreasing at -1, then we have a relative max at that point. Then since we're changing from decreasing to increasing at 1, we have a relative min at that point. Now also be careful of the way the question's asked in terms of how you give the answer. The critical value is the x-coordinate of that point, right? The critical value, -1 and 1. The critical point, it would be the coordinates of the point. So -1, -4, 1, -8. Those are our critical points. Our relative maximum is -1, -4. Our relative minimum is 1, -8. The location is the x-coordinate. The value of the function is the y-coordinate. So I could say I have a relative maximum at x equals -1, or at the point -1, -4. The relative maximum value is -4. I have a relative minimum at the point 1, -8, or at x equals 1. The value, the relative minimum of the function is -8, the y-coordinate. So be careful of the language that's used, the way the question's asked. Be careful in MyMathLab. If they ask you for the point, put in the coordinates of the point. If they just ask you for the critical number, the critical value, you're putting in the x-coordinate. A couple of other examples, just some different types of functions. So we're still just finding the critical values, we're finding the extreme values, right? Relative maximums and relative minimums. So just a couple of examples with some different types of functions. So number 3, f of x equals the cube root of x minus 2. Excuse my mess up on the 3 there. But as we typically do, and we're finding the derivative of this, so I'm going to write it as x minus 2 to the 1/3, right, to make it easier to find that derivative. So then f prime 1/3 times x minus 2 to the -2/3. And this is where, writing it in a proper form may be a little more useful. When we talked about before finding derivatives, how we said, 1/3 times x minus 2 to the -2/3. That's our derivative. That's perfectly fine. There's nothing wrong with writing it that way. But I'm actually going to now use this for a purpose. So it's in my best interest to maybe rewrite these without negative exponents. And if need be, put it in radical form, which would be even more helpful for evaluating this, right? But first thing, looking for critical values, we said we have to know where the function is either, the first derivative is either equal to 0 or undefined. So I want to make sure that my first derivative is written into a form that makes it easy to determine that, right? So we're undefined where x equals 2, right? So f prime of 2 is undefined. A critical value would be at x equals 2. Let me maybe write that. All right. So x equals 2 is our critical value. Yeah, never mind, I have it written underneath, I didn't notice. Okay, so critical value x equals 2. Now, using our test strip, but also notice too, our first derivative, if I set that equal to 0, that's what I was thinking about doing. If I set this thing equal to 0, and you're solving that equation, all right, look at that a couple of different ways. I could solve that equation by multiplying both sides by the denominator, that 3 times x minus 2 to the 2/3, which is still just going to give me 0 on the right side, and the left side would be 1. 1 equals 0 is not a true statement. I mean, there's no solution there. Also think about it this way. If you have a fraction equal to 0, when is a fraction going to equal 0? Whenever the numerator equals 0. And since the numerator here of that derivative is just 1, again, that's never going to equal 0. So that, a couple of different ways that you can make that observation, or at least that determination where the function is equal to 0, where is it undefined. In the case of a fraction, it's equal to 0 when the numerator is equal to 0. It's undefined where the denominator is equal to 0. All right. We've got x minus 2 as a factor in that denominator, so x equals 2 is our critical value. That's in this case where f prime is undefined. So when I set up my test strip over here on the right, there's f prime. I located or said at x equals 2 that our derivative is undefined. Now, in terms of determining relative max, relative min, that doesn't matter. I mean, whether it's equal to 0 there or it's undefined there, it's still a critical value. And I'm still going to have to check to see what's happening on either side of that value. Right? But whether it's 0 or undefined is not going to make a difference in that observation. But notice what happens in this case, and this is different from the last one that we looked at. I took a test point in each interval. So on the interval from negative infinity to 2, I chose 0. Of course, again, 0 is always convenient. Now, again, remember, we're plugging that into f prime. We're plugging that into this function. All right, so you plug in 0 into that thing, and you will get a positive value. Because 0 minus 2 is negative. The cube root of that would be negative, but when you square it, that is positive. And then the other part of that would be 1 over 3 times that positive number. And so that's what I mean by, just look at the function itself. If I plug in 2, or plug in 0, I get negative 2. Negative 2 squared is 4, and then the cube root of that is some number. I don't even care what it is. All I know is that it's positive. Times a positive 3. And then it's 1 divided by that positive number. Or, again, type that into your calculator, and you have a positive function value. But notice if I plug in 3, all right, so I take a value in the other side, or on the other side of 2 in this interval from 2 to infinity. I plug in 3. I've got 3 minus 2, which is 1. Right? Cube root of 1 squared is still just 1. But again, I get a positive first derivative. Right? So this first derivative is positive in both of our intervals, from negative infinity to 2 and from 2 to infinity. So we have a function that is increasing on both of those intervals. And there's the graph of the function. I went ahead and included it in this case. This is our function cube root of x minus 2. But we have a function that is increasing, right, up to 2, and then we're increasing again on the other side of 2. So there is no critical point here. Right? 2 is still a critical value, but there is no extreme value. There is no relative maximum or relative min because our first derivative did not change sign. So yes, I mean, there's no guarantee, just because you have a critical value doesn't mean you're going to have an absolute or relative max or min at that point. You just have to check and see what happens to the derivative. Number 4, an example with an e to the x, because we love our e to the x. F of x equals x times e to the 4x. Our first derivative, product rule, and now we should be to the point now we've got to recognize when that happens. So we've got a product of x times e to the 4x, and when we're looking for f prime, that's a product rule. Right? So finding f prime, x times the derivative of e to the 4x, which is 4e to the 4x. There's our chain rule. Right? It's e to the 4x times the derivative of the exponent, 4, plus our second, e to the 4x, times the derivative of the first, which is x, whose derivative is 1. So there's our first d second plus second d first, x times 4x, 4e to the 4x, plus e to the 4x times 1, if we want to include that. But that's our product rule. That's all that is. And I just rewrote it. So I said, okay, that gives me 4x e to the 4x plus e to the 4x. And then I'm going to set that equal to 0, which, putting it in factored form is going to be helpful there. So factor out the e to the 4x, leaves me with 4x plus 1. Setting that equal to 0, Now, my first factor there is e to the 4x, and we've mentioned this before. Where is that going to equal 0? Well, it's never going to equal 0 because remember, e is a number. E is a constant, approximately 2.72 raised to some power. It's a positive number raised to a power. It's always going to be positive, which means it's never going to be 0. So I don't have to worry about that factor. It's always positive. The other factor, though, 4x plus 1, yeah, that I'll set equal to 0, subtract 1, divide by 4, and here's our critical number, critical value, x equals negative 1/4. Okay. So then we set up our test strip, and on either side of negative 1/4, we plug a value into f prime. I chose negative 1, plug negative 1 into f prime. Now, again, I can plug it into the entire function here, or just use this factored form. And we know that this is always positive, we just said. So all I really need to worry about is this guy. And if I plug negative 1 there, I've got negative 4 plus 1, which is negative 3, which is a negative value. And then if we plug in 0, I would get a positive value. Right? So there's our intervals, negative infinity to negative 1/4. We have a negative first derivative, so our function would be decreasing. Negative 1/4 to infinity. We have a positive first derivative, so our function is increasing. And then since we're changing from decreasing to increasing, we have a relative minimum at x equals negative 1/4. Now, if I wanted to know the coordinates of the point, then we'll plug that into the function, into f of x. And you can get an approximation there, because that would be negative 1/4 times e to the 4 times negative 1/4, which is negative 1. And so I end up with negative 4 over e. You can approximate that. Right? So we can't, we're not always going to give exact values, but at least approximations. We could plug that into the calculator. Okay. And then an application. And we always like to finish up with a nice application. So in this case, the number y of downloads of an app in thousands is related to the price x in dollars of that app by the equation y equals 2.6 minus 0.4x. Right? So we've got the number of downloads represented by our function in thousands. X is the price of the app in dollars. So question part A, find the revenue, R of X, okay, generated when the price of the app is X dollars. Right? And we've talked about revenue before in terms of, if I have, in this case, we said the number of downloads, the revenue would be whatever the cost of the item is times the number that you sell, or in this case, the number of times the app is downloaded. So the price of the app, X dollars, number of downloads, which is our function, Y, so our revenue would be X times Y, right? The number of downloads times the price of each download. So I've got X times our function, 2.6x minus 0.4x squared. There's our revenue function, right? And then question part B, we're looking for the relative extrema of that revenue function and interpreting what that tells us, right? So this is kind of leading into what I said early on, using this in the context of applications, right? So once I find those extreme values, well, what information does that actually give me about the function? So here's our derivative r prime, and we start with that if we're looking for our extreme values, our critical values. Setting that derivative equal to 0, solving for x, and I get 3.25 in this case. Here's our test strip. I chose value on the left and right of 3.25. I chose 0 and 4. Plug that into r prime of 0 would give us a positive value, right? Just 2.6 actually. R prime of 4, plug that into our derivative, and that will give you a negative value. You can double check that calculation. 4 times 0.8 is 3.2. Subtract, and that would give us a negative value. So we're increasing on the interval from 0 to 3.25. We're decreasing on the interval from 3.25 to infinity, which means that our function would have a relative max at that x value, right? Changing, or first derivative changing from increasing to decreasing. So at x equals 3.25, we have a relative maximum. And the value of the function there, if you plug 3.25 into the function, now again, be careful because we are working with different functions here. The function r, the derivative r prime, I want to know the actual value of the function, so I'm plugging that into r of 3.25, and you get 4.225. Now, what is that in the context of this problem? Well, again, what was r? R was the revenue. X is the price of the app, revenue in thousands of dollars, and X is the price of the app in dollars. And since R is the location of a relative max, or at that point where X equals 3.25, then that would be a maximum value of our function. Or in this case, it's the maximum revenue. So the fact that there's a relative max there tells me that we have a maximum revenue in thousands, $4,225, 4.225, when the app price is $3.25. Right? So these are the types of applications that we're going to be dealing with going forward. Finding what we call these optimization problems, where we're looking for the maximum value of a function or the minimum value of the function, and we know that those could occur or will occur at these critical values. So these are the tools that we'll need to do that. We find our critical values, we check the value of the function at that critical value, determine if it's a relative max or relative min in the context of our application. Okay? So that is section 3.1.